In this video, we're going to discuss diagonalization. So let's start with a definition. A square matrix A is diagonalizable if there exists an invertible matrix P and a diagonal matrix D so that P inverse AP is equal to D. So a classic example for this topic is to find a matrix P that diagonalizes a given square matrix. To do this, we're going to find a basis for each eigenspace. And once we've got that, we'll figure out how to build the matrix P from there. So let's look at our matrix A. Notice that it's upper triangular, so it's particularly easy to figure out what our eigenvalues are. The eigenvalues are going to be the numbers on the diagonal. That'll be true anytime you have an upper triangular, lower triangular, or diagonal matrix. So you just grab your diagonal entries there. So let's start with the eigenspace E2, and we're going to try to find a basis for the eigenspace. So to find the eigenvectors, we're going to solve the homogeneous system, where our coefficients are a minus lambda I, so in this case a minus 2i. So let's subtract 2 from the diagonal entries of A, and there we have our system. So we're going to put this into our REF and solve. So you could check with a little bit of work that our REF comes out looking like this, and let's go ahead and solve our system. So since we're finding eigenvectors, we'll just call our variables x1, x2, x3. Can go through the rows here and circle the first non-zero entry in each row, and that leaves x1 without a circle. So x1 is going to be t, and then top two rows of our matrix say that x2 equals 0 and x3 equals 0. So we could write down our eigenvectors in vector form. We would have 1, 0, 0 times t. And strictly speaking, the 0 vector is not an eigenvector. So if you were just writing out all your eigenvectors, you would just say we should not include the 0 vector. So basis for E2, just grab your set of direction vectors. In this case, we've just got a single vector, 1, 0, 0 in that basis. So now we're going to go through the same kind of process for E3. We're going to find our eigenvectors. So we're going to be solving a homogeneous system. Coefficients are a minus lambda I, so in this case a minus 3i. And I think I'll write the matrix A just over on the side here so that we can see that. So to get our coefficients, we're just going to subtract 3 from the diagonal entries of A. And we want to put this into our REF so that we can solve. In this case, it would just be a matter of multiplying the top row by -1, and then we're ready to solve. So we could call our variables x1, x2, x3. Now let's figure out what our eigenvectors look like. So going through the rows of the matrix and circling the first non-zero entry in each row, we've just got a single circle, meaning x2 and x3 are both going to get parameters. So let's say x2 is s, x3 is t, and then top row says x1 plus 2x3 equals 0. So if we solve for x1, we would say x1 equals minus 2t. So from here, let's write out our vector form, and then we can write down a basis for our eigenspace. So our eigenvectors x are going to look like this, something times s plus something times t. We'll just fill in our coefficients. So for x1, it's 0 times s minus 2 times t. x2 is s, so 1 times s plus 0 times t. And x3 is t, so nothing times s plus 1 times t. And if we were being really careful here, we would say technically we don't consider the 0 vector to be an eigenvector. But since we're going to be moving into writing down a basis for the eigenspace, we don't really need to dwell on that. Okay, so basis for the eigenspace E3, we'll just pull out our direction vectors, and this time there will be 2 of them. So 0, 1, 0, and -2, 0, 1. So let's look back at the beginning of the problem and just figure out what we're trying to do here. So we're trying to find a matrix P that diagonalizes A, and we said we should find a basis for each eigenspace. All right, so let's write down what our basis for E2 was. We had it right here, was 1, 0, 0. So I've just recopied that information, the basis for E2, so that we can see everything all in one place. And now we'll figure out how to build the matrix P. Here are our instructions on how to finish the problem. So we're going to put all the basis vectors that we found into the columns of P. We can put those in any order that we like, as long as we fill the 3 basis vectors into the 3 columns of P. And then the diagonal matrix D has the eigenvalues on the diagonal in the same order as P. So meaning you can fill the columns into P in any order, but once you've decided on that order, that will determine the order for the entries of D. So let's do a couple of examples of that. Okay, so building our matrix P. So first, I'll just grab the basis vectors, write them down in the order that we found them in. So we found 1, 0, 0 first. Then we did the basis for E3, which was 0, 1, 0, negative 2, 0, 1. So there's our matrix P, and technically the question is answered. But just for the sake of discussion, I'll show you the diagonal matrix D that gets produced. So D is going to be diagonal, meaning all the off-diagonal entries are going to be 0. And the only question is what is on the diagonal. It's going to be your eigenvalues, which we know are 2 and 3. And they're just going in the same order as the columns of P. So 1, 0, 0 was an eigenvector corresponding to 2. So 2 is the first entry. 0, 1, 0 corresponds to the eigenvalue 3. So that's the next diagonal entry. And then negative 2, 0, 1 corresponds to, again, eigenvalue 3. So that's your third entry. Okay, now someone else could come along and build a different matrix P. So they could say, I don't feel like doing P in that order. I want to choose a different order. So maybe they want to put negative 2, 0, 1 here, and then 1, 0, 0 here, and then 0, 1, 0 there. That's totally fine, but that's going to impact the diagonal matrix that they're producing. So D is still going to be diagonal, but the order of the eigenvalues is now changing. Negative 2, 0, 1 is associated with the eigenvalue 3. 1, 0, 0 is associated with the eigenvalue 2, and then the last one is associated with a 3. So you change the order of the columns of P, that's fine. You're just going to be changing the order of the diagonal entries on D. And of course, D has zeros in all these other positions. So I think just for the sake of giving a single answer, I'll stick with the top possibility here. So at this point, we're done the problem because all we needed to do was build the matrix P. But I point out the matrix D just in case we wanted to do a check. So this part is optional, but it does help reinforce the idea of what we're doing. So if we wanted to check that we had done this correctly, we would need to find the matrix P inverse. And a good way to do that is to just take your matrix P, put the identity beside that, do some row operations, and create the identity matrix on the left. You'll get P inverse on the right. Often, P turns out to be a relatively simple matrix, so usually this process of finding the inverse, sometimes it's only 1 or 2 steps. Okay, so let's say we could find P inverse pretty quickly, and then the main equation that governs diagonalization is that P inverse AP equals D. So if you wanted to check that this process really works, you could calculate P inverse times the original matrix A that we started with, times this matrix P that we just built, so P inverse AP, and confirm that it really does give this diagonal matrix D. So just a quick note here to clarify some details, just if we were being very careful here. I would point out that when you take bases for different eigenspaces and you combine them, like we've done here to build P, the new set is guaranteed to be linearly independent. So we saw that in section 4.3. So what that's saying is this 1, 0, 0 was your basis vector for E2, and these guys together formed the basis for E3. Guaranteed when we now throw them together into a set of 3 vectors that they're all going to be linearly independent. The reason why we care about that is because if you then have a set of 3 linearly independent vectors in R3, the fundamental theorem of invertible matrices guarantees that that matrix P will be invertible. So the whole point of this discussion is just to say P will always be invertible. You'll never run into a situation where this matrix P that we build doesn't have an inverse. Guaranteed to have an inverse, and therefore this formula P inverse AP equal D will always work out once you've built your matrix P. So here's a fact that will tell us exactly which square matrices are diagonalizable. A matrix A is diagonalizable if and only if the geometric multiplicity is equal to the algebraic multiplicity for all the eigenvalues. So now we're going to do an example to see what can go wrong. We're going to see a matrix that can't be diagonalized. So the question says to diagonalize A, or this is sometimes worded as find the matrix P that diagonalizes A, really comes down to the same thing. So first thing we would do is figure out our eigenvalues. In this case, we've just got a single eigenvalue, lambda equal 4. We know that because A is lower triangular. So we're able to just pick out the eigenvalues as being the numbers on the diagonal. Okay, so let's work on finding a basis for E4. We would solve the homogeneous system, A minus 4i. And so we'll subtract 4 from the diagonal entries. That leaves us with this little matrix here, and strictly speaking, should put that into our REF before we solve. So that would just be a row swap there. And then we could go ahead and solve for our eigenvectors. So if we go through the rows of this matrix, we circle the first non-zero thing in each row. We see that x2 is going to get a parameter. So already we could figure out that something has gone wrong. We've got a single parameter here, which looking ahead, that means there's going to be a single basis vector for this eigenspace. And that means we only have one basis vector to work with. So when we try to build our matrix P, it's only going to have one column in it. That's not going to work. That's not going to be a 2 by 2 matrix. So somehow we don't have enough eigenvectors. And that's exactly what's going wrong here. So let's go a little bit further and figure out some of the details. So first row says x1 equals 0, and then we can write down our eigenvectors in vector form. So they would look like 0, 1 times t. If we were just talking about eigenvectors, we would say, well, technically the 0 vector is not an eigenvector, but we usually move quickly on from there and just actually talk about the basis instead, because it's faster to write down. So basis for E4, just pull out all your direction vectors. In this case, there's just a single direction vector, 0, 1. So we just had one eigenvalue. When we looked into that eigenspace, we just found one basis vector. And so we can conclude that we can't build P. There are not enough basis vectors. So whenever this happens, this implies that you can't diagonalize your matrix A. So not every square matrix can be diagonalized. Sometimes people will give you a question like this and say, find P that diagonalizes A, or they'll say find P if possible. And this is one of those situations where it's just not possible. So let's put this discussion into more technical language, and we'll try to understand what's gone wrong here. So I'm just going to draw a line because technically we've finished the problem, but we're now going to look at the details and practice some of our terminology for linear algebra. So let's think about the characteristic polynomial, or the characteristic equation for this particular matrix A. So remember, the characteristic equation is just where you take your determinant of A minus lambda I, you set that equal to 0. Because A was lower triangular here, if you just subtracted lambda from the diagonal entries and then you took the determinant of that matrix, you'd have 4 minus lambda all squared equals 0. So the algebraic multiplicity of lambda equal 4 is 2. Remember, algebraic multiplicity just refers to what is the exponent on the relevant factor in the characteristic equation. And then the geometric multiplicity of lambda equal 4 is 1. Geometric multiplicity is talking about how many basis vectors do you have in that eigenspace. Well, we found our basis for E4 up here, and there was just a single basis vector. So the fact that the geometric multiplicity is strictly less than the algebraic multiplicity is just a very technical way of saying we don't have enough basis vectors. We can't build P. So if your geometric multiplicity is less than your algebraic multiplicity for any of your eigenvalues, then you can't diagonalize A. If you rephrase this statement in a slightly different logical way, you could say, or let's say if A is diagonalizable, that implies that the geometric multiplicity must be equal to the algebraic multiplicity for all your eigenvalues. So for every one, you must have enough basis vectors in that eigenspace. So we talked about which matrices are diagonalizable, and we've talked about how to build the matrix P that diagonalizes a matrix. Now we're going to get into the second half of the video, which is why do we care about diagonalization? So let's do a quick example here. We're starting with a diagonal matrix. That's important, and we're going to square it. So just multiply it by itself in the usual way, and what we end up with is this matrix here. Now what's special about this is if you look at what we've got on the diagonal here, at the end of the calculation we've produced a diagonal matrix, and specifically on the diagonals we just got the squares of the numbers that we started with. And this is illustrating a fact that's going to be true more generally. So if D is a diagonal matrix, then when you raise D to a power, D to the n, you're getting a diagonal matrix with the nth powers on the diagonal. So just to do another quick example of this, let's say you have the matrix -2, 0, 0, 3, which is diagonal, and let's say you raise that to, let's say, the 5th power. What you're going to get is a diagonal matrix. On the diagonal, you're going to have the 5th power. So -2 raised to the 5th power, -32, and 3 to the 5th, 243. So it's particularly easy to calculate powers of diagonal matrices. That's what we're getting at. So here's a really key fact for us. If we have P inverse AP equal D, in other words, if we've managed to diagonalize our matrix A, then we have a quick formula to help us compute the nth power of A, and that is P D to the n P inverse. This would be true for any positive integer n. So just to write an interpretation underneath this, let's say this is a quick way to compute A to the n. Because if you just have some square matrix that's not diagonal, let's say matrix 1, 2, 3, 4, and I say, okay, let's find, the power, the 100th power of that matrix. That's not going to be a quick thing to do. We have to multiply A by itself 100 times. Yet this formula here makes it considerably quicker. So let's just ask, why should this be true? Well, we're going to start off with the fact that P inverse AP equals D. So assume that we've found the matrix P that diagonalizes A, and assume that we know the matrix D already. So we have all these ingredients. Let's think about solving for A. So we would multiply by P on the left side. We'd have P times P inverse AP equals P times D. And on the left side, the P and the P inverse will multiply together just to give us I. I times any matrix gives us that original matrix back. So we've just got AP now on the left. Okay, let's multiply on the right by P inverse. So we have to bring P inverse in on the right so that it's actually touching the P, and therefore it has to come in on the right side of this expression as well. So P times P inverse equals I, and therefore A times I is just going to give us back our original matrix A. So what we've figured out is that A is the same thing as P D P inverse. Okay, now imagine that we multiply A by itself a whole bunch of times. So A to the n. Well, since A is PDP inverse, this is like going PDP inverse, that's A, times another PDP inverse, that's another A, and just keep doing this, however many times, n times. Now the idea is that we're going to have a lot of cancellation on the right side, because notice that you've got a P inverse times a P. Here you would have another P inverse times a P. Here you would have another P inverse times a P. So every time you see P inverse times P, that's giving you the identity matrix. And the identity matrix times any matrix just gives us back that original matrix. So in other words, this right side really simplifies. We get a to the n equals, well, you'd have a P in front, you'd have a P inverse at the back, but in the middle, you've just got D times D times D a whole bunch of times. In fact, we know exactly how many times. It's n times. So P, D to the n, P inverse. All right, so that's the formula that we wrote down. So then now we can still ask, okay, why do we care? Why is this formula actually easier? Why is this right side easier than just calculating a to the n the long way? Well, remember our fact from a minute ago, really easy to compute powers of diagonal matrices. So d to the n is easy to calculate, and then it's just a matter of multiplying by p on the left, p inverse on the right, and you've got a quick way to calculate a to the n. So let's see this in action. So here we're told that the matrix P diagonalizes A to produce the given diagonal matrix. What we want to do is find a formula for a to the k. So our answer is certainly going to involve k, as this exponent here is unknown. So the formula we're going to be using here is the formula we just talked about. A to the k is going to be p d to the k, p inverse. And so we have a couple of things to figure out before we can really plug into this formula. We need to figure out what does d to the k look like, and we need to figure out p inverse. So let's work on both those things first, and then we can plug into this formula. Okay, I think I'll start with p inverse. So to get p inverse, let's write down what we're doing. To get p inverse, we're going to write down p and the identity matrix. We're going to do some row operations and turn that into the identity matrix. P inverse will come out on the right side. So there's our matrix P, write down the identity matrix beside that, and there's just going to be one row operation required to get the identity matrix on the left side, which is to do row 1 minus row 3. So it's just that third column that has to be cleaned up. So in our top row, that's going to create 1, 0, negative 1 on the right side. So now that we've got the identity matrix on the left, we can say this guy here is P inverse. So that part's usually pretty quick. Now we can figure out d to the k. Remember, d is a diagonal matrix. On the diagonal, we had 3, 3, 4. And we had a fact that said if you are trying to raise a diagonal matrix to a power, all you have to do is exponentiate the diagonal entries. Really fast way to compute powers of diagonal matrices. And now we've got all our ingredients ready, so I'll highlight the two things we're going to be using. Got our P inverse here, got our d to the k here, and we can now put it all together. So our big fact said a to the k is equal to P d to the k, P inverse. Now remember, bracketing order doesn't matter here, so you could either do this multiplication first, or you could do that multiplication first. Doesn't really matter. I suppose I'll just work from left to right. So we'd have 3 to the k, 0, 4 to the k, 0, 3 to the k, 0, and then 0, 0, 4 to the k. So we multiply those first two matrices. We still need to multiply by P inverse, and then one more multiplication to get our answer. So we're going to have 3 to the k, 0, and then this entry here is going to be minus 3 to the k plus 4 to the k. So that might look a little bit better. If we write the positive term first, let's call it 4 to the k minus 3 to the k. And then we have 0, 3 to the k, 0, and 0, 0, 4 to the k. And that's our final answer. We have found a formula for a to the k. So just as a follow-up to illustrate why we care about this, for example, now that we've got this a to the k, it's really fast for us to plug in any exponent and figure out what that power of a is. So if we use k equal 5, we'd have, well, 3 to the 5 is 243. 4 to the 5 is 1024. In the top right, we have the difference, so it's 781. And we've got zeros in these positions. Similarly, if someone asks you to compute, say, a to the 100 or a to the 350 or whatever, very quick to do that computation once you've got this nice formula for a to the k. So I wanted to take this further into the real world by showing you an application of powers of a matrix. This won't be tested, it's really just to give you a bit more intuition, a bit of insight into how you might actually use this in the future. So we'll just do one example here. Consider a manufacturing plant with 1,000 machines. So we're going to have two categories here for the machines. W will be the category that a machine is working, and B will be the category that a machine is broken. Collecting a bit of historical data over time, we could come up with a probability matrix. So let's figure out how to interpret this. So the columns here represent the state today. So this column represents machine is working today. This column represents a machine is broken today. And then our rows represent the category tomorrow. So the first row represents a machine is working tomorrow, and second row, machine is broken tomorrow. So what we have actually inside this matrix are probabilities for moving from state to state. So let's say a machine is working today, 99% probability it will be working tomorrow, 1% probability that it will be broken tomorrow. And of course, these numbers in this column should add up to 100%. If a machine is broken today, 50% probability it'll be fixed by tomorrow, 50% probability it will stay broken. So that seems reasonable. That's our probability matrix for moving one day into the future. Then we could have a state matrix just representing what's going on today. So let's say today is a good day. All machines are working today. We're going to represent our state matrix in a column, working and broken. So 1,000 machines working, 0 machines broken. And in terms of notation, pretty conventional to call our state matrix X and to call our probability matrix A. So those are the ingredients that we need. And from there, we can predict what's going to happen in the future. So if we want to predict what's going on tomorrow, it's just going to be a matter of taking the matrix A and multiplying by X, because X is representing what's going on today. Multiplying that by A moves us one day into the future. It takes us from today to tomorrow. I think I'll write out the details here just so we can see this happening. So here's our matrix A, and we're going to multiply that by our state matrix, 1,000, 0. So the categories, remember, have to match up. If you got working, broken, then you have to have working, broken in that order. So we were careful to set it up that way. And we can just multiply this out. And you can confirm, yep, 990 working, and it'll be 10 broken for tomorrow. If we wanted to look 2 days into the future, then we just need to multiply by A again. So that would look like A squared times X. If we wanted to look 3 days into the future, A cubed times X, etc. So X just always representing your starting point or your state matrix today, A to the N jumping you N time periods into the future. So in this case, A to the N is jumping you N days into the future. So in a real world context then, people often do long-term modeling and they say, okay, well, at the end of this quarter, 60 days from now, 90 days from now, a year from now, what kind of state are we looking at? Are we going to have a situation where almost all our machines are broken? Are we going to be in a pretty good scenario? Are we going to have a lot of fluctuations week to week? So this long-term prediction is pretty important. Therefore, you can ask, as n goes to infinity, what is a to the n times x going to look like? And so that's a question involving very high powers of a matrix and a very applicable problem. So it turns out for this machine problem, as n goes to infinity, a to the n times x starts to approach 980, 20. So the situation stabilizes, and in the long run, you'll have 20 machines broken each day. Now, they won't be the same 20 machines. Some of those broken machines will get fixed, other working machines will break, but the actual number of broken machines stabilizes, and long term, you're going to have 20 broken machines each day. So that's really powerful knowledge, and it's the power of the matrix that helps us get that knowledge. So this is why diagonalization is so important. So that's our video on diagonalization. Thanks for watching.